Cool. All right, so let's go ahead and get it open. All right. Unfortunately, we're going to be hearing bad heater because we're in Canada in January. It's cold as can be outside. Okay. I don't know how this was repackaged, so it's just going to be. Oh, there's some plywood in here. Chipboard. Cable and a key. Okay, so what do we got? More garbage, more garbage, more garbage, more garbage. These things are useless. Okay, they're alright for short-term shipping, but they deflate easily, and over time, if you just leave them, like they lose their air, they're no good for packing stuff like this. Good hard styrofoam, paper, cardboard. That's the kind of stuff you want. This stuff's really great. Okay, so that's the umbilical for the laser. This thing looks very dirty, and that scares me a little bit, but I'll reserve my judgment until I get the thing out of the box and kind of figure out what's going on with it. And I just realized I don't know what I'm going to do with this thing. I've got nowhere to put it right now. I don't really have a good space for it. My table is a little dirty. I don't know how heavy the head is. It's quite heavy. Yeah, this is going to be a little hard to get in and out of this thing. Not exactly the cleanest box either. Okay. Alright, well, it's not the end of the world, kind of heavy, but it's still kind of heavy. Okay. What are we going to do? We're going to get this thing out of here. Camera is in the way. We're going to have to change sides of the camera and get my hydraulic cart over here. Yeah, that's totally what I got to do. Okay, so let's do that. I have a plan. Fear not. Okay, let's give this a shot. I'm going to for the entire thing together, but we'll just test off. Yeah, we can. Alright, so that's not good. Not like it. Not like it at all. Okay. Alright, well, this is okay. Alright, victory! The Vitesse is on the thing. Half of it. I have to get the other half on there. How the hell are we going to do that? Is the Vitesse. That provides the pulses to the amplifier, which is behind us now. This is a control electronics. I don't know exactly what all is in here, but this talks to here a little bit and performs. So on this side, I believe, is the green pump laser. On this side is the resonator cavity where the ultra-short pulses are generated. In here is a single pump diode, and it's coupled through an optical fiber through the black umbilical back. And then there's a bunch of cables that sort of connect the laser head to the laser controller. And that's all I know. It's got a couple of internal menus and options. Their manuals are available for this online. This is quite an old laser system. I believe this one is dated 2002. Sorry, March of 2004, and it produces 2 watts at about 80 megahertz. So each pulse from this thing is extremely low energy. I think that's on the order of maybe 10 or less nanojoules per pulse. It's a pretty low energy. Whereas this laser behind, this seeds the amplifier. The amplifier only produces, say, 1 to 2 watts of output, average power, but the pulse energy on this thing is 300 microjoules, so it's many, many orders of magnitude more energetic in each pulse than this thing is. And that's important for micromachining applications, which I will talk more about later. So the first thing I want to do is get a peek under the hood for this thing and the power supply to really understand if there's just anything simply exploded in either of them. To do that, I'm going to need a couple of Allen wrenches. I don't know what they are, if they're metric or standard. They're smaller than what I have in a T-handle though, that's for sure. Oops. Yeah, I think they're going to be metric. Or standard. Yeah. Okay, well I have a set of those. Okay. I have to turn this to get into it because I need to take screws off the side too. Now, someone other than me has been inside of both of these components at some point, and I don't think it was a Coherent rep. I think it was a DIYer. So that's where we're at. I don't know what this came out of. It did not, well, as far as I understand, this never came out of a Libra. This was part of maybe some kind of microscopy system or some sort of biochemistry or chemical analysis system. So that's kind of what I think this came out of. And I have no idea what that means it would be used for. I'm guessing some sort of spectroscopy application, taking measurements on samples. But no matter, that's not what we want it for. We want it for much more exciting purposes. Okay. Cleaner, specifically for this purpose. Putting these screws in. Okay, and get into the other side, a little more interesting. An angle here. There's the last couple screws out. Open up the chassis and see if any electronics are obviously dead or exploded in here. And that would be tragic. Or frankly, it may not actually be the end of the world. It might, if that was all that it took to fix it, that would be great. Some of the other options are very, very, very expensive. All of this schmutz is corrosion, I believe. And I'll zoom in for a second. Okay. I believe this is corrosion on the surface of this other heatsink, the unused heatsink, okay? And You can see signs of water damage in other places here on these amphenol connectors, okay? If you look really closely, this corroded interlock switch here. Alright, and some more corrosion right here on this nut. Some corrosion along the side of this diode module. You see here the green. So there's definitely over here in the bottom left. So something naughty has happened with this thing. And sometimes electronics just survive that kind of mistreatment. Unfortunately, sometimes they don't, though. So apparently it does plug in, it does turn on. It hasn't failed in that regard. I mean, ultimately, what's gonna tell what happens. So this is the diode module here, okay, and light is coupled out of this into this optical fiber, and through this optical fiber, you see someone's been in here and touched this at some point, messing with the fixed point on this fiber. This should be located probably here, I believe. And I'm thinking that this fiber should also be clipped into these points. So someone else has been in here and has looked at the output spectrum. Yeah, because this isn't properly tightened anymore. Someone else has messed with this thing. And it was not me. And that is a little bit concerning. I don't really want to dig into the rest of it until I know if it even powers on. I mean, if I plug it in and it turns on, then I probably won't bother touching it. Something that's definitely going to need love and repair or replacement is this. There's a battery backup unit here, so that if the system loses power, inside of the actual Vitesse itself, there is a crystal. I believe it's LBO, and that crystal inside of the Vitesse, there is a crystal, and that generates the green light. So we call it a second harmonic generation crystal, SHG crystal. So it's taking 1064 nanometer laser light, which is generated in the pump cavity. So it takes the light from, sorry, let me restart here. Inside of the Vitesse, we have a laser crystal, I believe it's YVO, is pumped by around 808 nanometer laser light. So that's what's coming out of this optical fiber here and comes from the diode module, this diode module right here, okay? So electrical power converted into visible radiation, piped in through this. I believe this is something like 12 or 18 watts. I could be wrong, but something like that. I'll get a power measurement on it at some point soon. Then, once it comes out of sort of this end of things, it goes into the laser head. There is a crystal, which is pumped by this laser light, 808 nanometer laser light, pumps the YVO crystal. I believe it's ytterbium, or maybe it's neodymium YVO. Yeah, neodymium YVO, I think is what it is. That generates light around 1064 nanometers, and then that's converted to, it's either, I believe it's converted to 532 nanometer. There are some different wavelengths here that I'm working with, depending on the laser crystals that are used inside of this laser. These might be slightly different. Instead of being 1064, it might be, what's the wavelength? 1027 and then, or is it 1032? So there might just be some variations in the wavelength that's actually used in here. But in principle, the 1000 nanometer-ish wavelengths are invisible to the eye. You can't see them at all. This 808, you could maybe see a very faint glow, but it would have to be enormously bright, and it would be extremely dangerous to view this with your unprotected eye. And then, so you pump the crystal in here with 808 nanometer, and then That converts to green light with the second harmonic crystal, and then that green light pumps the titanium sapphire crystal and it outputs the actual pulses. Now, the thing I'm trying to get at is that LBO crystal is heated. It's in an oven, and that generates basically a higher conversion efficiency from the infrared radiation into visible radiation in green. Now, the problem with that is that once you heat that crystal up, if you drop its temperature too quickly, you can damage the crystal. So, when I mentioned the battery backup inside of here, okay, the battery backup, this one, I believe, is designed so that if this system loses power, this has enough juice in it and the control board smart enough that it just runs the heating element in the crystal long enough on battery power so that it can slowly ramp its temperature down so that it doesn't damage the crystal when it cools off too quickly. So that's kind of the whole point of the battery backup. So pretty important. You can run it without it if the battery's no good, but it's really, really good idea to have that in place, because if you ever lost power or for whatever reason, you'd have to regain power really quickly in order to avoid damaging the crystal, or at least avoid risking damaging the crystal. So, and those crystals can be very expensive to replace, as we may find out. Okay, so now that we've had a peek inside of the power supply system, my hopes are maybe a little diminished just because of how much water damage I see in here, but apparently it does turn on, so that's good news. The majority of it shouldn't be damaged. The next thing we have to tackle is keeping this heater from driving me nuts. The next thing we have to tackle is getting into the Vitesse head, the actual meat and potatoes. We're about to open up the Vitesse for the first time. This is going to be many months of pain, I can already tell. Okay. Slowly coming. There we go, a little more. And what do we see? What I thought I would see. When I was talking about what each component does, this here is the green laser, okay? So, let's see here. Infrared light comes from this laser diode. It's around 808 nanometers, somewhere in between there, okay? That light is coupled into this optical fiber through here, okay? Goes through the umbilical, comes up through the umbilical on this side, into this laser, which is the metal box below here, okay? In here, it generates around, say, 1064 nanometer infrared light. Is inside that same cavity converted to green light at 532. Green comes out, bounces off this mirror, is reflected into this cavity here. This is where the titanium sapphire crystal is, and this is where we convert green light into, again, 800-ish nanometer light, but it's very broad spectrum. This is a mode-locked laser, so it produces extremely short pulses of light, and it does that in a very, very short cavity, very, very small distance, and so it produces pulses very quickly. So its repetition rate is 80 megahertz or so. And that's fine, because we want low energy pulses to see the amplifier, which is behind the camera. So those bounce around inside of here, and then eventually are emitted at an exit aperture, and then routed through a couple of mirrors, and then out of the laser. There's a shutter here which controls the output of light from the laser itself. So this laser is actually 3 separate lasers working together. There's the pump diode, which is a laser diode, okay? Then there's the green laser, which is a 2-watt green laser, which pumps the, very roughly, approximately 2 watt. And then there's the actual seed-producing laser, which is, also produces output of around, I believe it's 1 watt. There's a bit of loss here, so as you know, this thing, maybe 20 watts, say, or 18 watts. This only produces 2 watts, and then this produces, maybe 75% of what you put into it, this laser. So this is maybe producing, say, 1.5 or approximately watts here in terms of average output power. So that's kind of the inside of this thing. Oh no. That's the insides. So now we're going to zoom down in here. So this mirror has a set of piezo drives on it here, and they're actually powered off of this, and I guess there's some sort of piezo control board here. And this laser is smart. It sort of talks to itself and it asks, you know, okay, how much power output am I producing? And the controller, this box, says not enough. Try tuning your mirrors this way, that way. And then it runs an algorithm, a feedback loop, to see if tuning the mirrors is increasing the power one way or another. And then it will sort of automatically optimize by tuning this mirror a little bit here. It's where the beam enters the resonator on this side, and that will help maintain the automatic sort of alignment of this laser to this laser. And so that produces a very stable output intensity, which also helps maintain the stability of your amplifier. But as you can see, there are manual rotation knobs on this. So in theory, you can actually manually tune the alignment and turn off this sort of servo feedback automatic updating thing if these piezo drives fail. So talking to some people in the industry, they suggested that I check the piezo drives to see, hey, is it the piezos that have a problem maintaining the alignment? So if these piezos are dead, then this is a pretty easy fix. So I guess really the first thing to do is to confirm over here. We confirm that first thing to do is we'll confirm that the power output from the diode module and the spectrum from the diode module is correct, assuming this thing turns on. If that's fine and that there's no issue with the diodes, okay, then we turn to the green laser over here. And if the green laser has problem, like let's say once we get the power supply checked out, everything's good, we're getting light into the green box, okay? If our green laser doesn't produce light, well, we know we have a problem. So then we have to open this up and see where that issue is occurring inside this laser. If this produces green light, we may not have such a big problem, but it might still not be great. The next thing I can do is put a mirror in here and catch this beam and bounce it out, measure its power, see if it's what it's supposed to be, see if it's stable, and then measure what the beam profile looks like so we can see what the mode coming out of this laser looks like. It should be Gaussian in shape, okay, an intensity profile. If it's not and it's got a bit of an odd shape, that might be a big issue for this thing. It doesn't like sort of crappy looking pump light. So I'll have to take a look at that. But if everything checks out here and there's still an issue with this thing working, it's very possible that it is this piezo controller right here, or the piezo drive, so I can try to disable that in the software. And then if we kind of trace everything down to here, and this is the last component that's not working, this could be pretty interesting to try and fix, because it has a titanium sapphire crystal in it, and usually those crystals don't go bad, but there could be an issue with the alignment inside of this cavity or something else more sophisticated in the control electronics that I'm missing and I don't understand. But in principle, there's a laser diode. Check if that's working or not. Confirm all the electronics are working correctly. So checking that laser diode requires me to look at the spectrum and its output power. If that passes and electronics pass, then we come to this box here. If this box passes, it's producing green light, that's okay, that's great. If this mirror is not performing correctly, we don't get any green light out of it, well then, okay, there's the mirror. But if the mirror passes, that's good. Now we're onto this thing. That's where it gets more complicated. That's kind of the plan right now. And I'll have a little more information and some more things to follow along in this story soon. Okay, thanks a lot.